Welcome to reaction rates. So, we've already discussed the thermodynamic concepts such as change in enthalpy, which is how much energy is absorbed as heat during a process. But while thermodynamics explains what processes are spontaneous, so which ones will happen without us driving them by putting in energy in some way, it says nothing about how fast these processes occur. Right? Thermodynamics only talks about whether or not a process will occur, not how long will it take to occur, and that's what we're interested here with kinetics. And we're going to talk about reaction rates. So, chemical kinetics is the study of reaction rates. How fast a reaction happens, how fast some process occurs. The reaction rate is how quickly a reaction proceeds. So, it's usually defined as a change in concentration of a reactant or product per unit time. So it may look something like this. So the reaction rate is equal to a change in concentration, in this case some concentration of some species A, over some change in time. So we can write that way as a change in concentration over change in time, or we can write it this way as concentration of our species A at time 2 minus the concentration of A at time 1 divided by time 2 minus time 1. So let's look at the decomposition of nitrogen dioxide. So we have 2 NO2 gas, decomposed to yield 2 NO gas, and 1 oxygen molecule. So we can define a reaction rate either by our reactant, the nitrogen dioxide, by our product, nitrogen oxide, or by our other product, oxygen. So we can define it either as a change in NO2, a change in NO concentration, or a change in O2 concentration. So let's plot our concentrations of the reactants and products over time. We'll do that over here. So you can see that as we have our time on the bottom axis, the x-axis, and on the left axis we have concentration. You can see that over time our NO2 concentration is dropping, our NO concentration is increasing, and our O2 concentration is increasing. So again, we expect the NO2 concentration to decrease with time because it's a reactant. So over time we're going to use up our reactant. And so our change in NO2 concentration is negative, whereas our change in oxygen concentration would be positive, and our change in NO concentration would also be positive. So we know our change in our reactant concentration is negative, but this makes the reaction rate negative. And we don't want a negative reaction rate. We want to be discussing our reaction rate in positive terms. We don't want to be saying that it happens negative some number of times per minute or something. So, in the rate expression for a reactant, then we need to include a negative sign. So, our two products, the NO and O2, we're going to leave alone. We're not going to change those reaction rate expressions at all. But we're putting in this negative sign here for the NO2 because the NO2 was a reactant. So, now note that the slopes of the concentration versus time curves on this graph are constantly changing because initially we have a very fat, a very high negative slope in this case, or a high positive slope in this case, and later on the slope becomes less and less. Now we expect this to happen because over time, or at least initially, we have a lot of NO2 around, so we expect our rate to be fairly high. In order to have our reaction proceed, we need to have our NO2 molecules, we need to have 2 of them collide with one another. Well, the higher the concentration of NO2 is, the higher the rate should be, because the faster we'll have NO2 molecules colliding with one another. And later on, when the concentration becomes lower, then the rate at which those NO2 molecules are hitting each other becomes lower. So we expect the rate to be less later on. So, also note that the decrease in NO2 concentration is matched by an increase in NO concentration in a 1-to-1 ratio, because for every NO2 that decomposes, we get 1 NO molecule formed. Now, the O2 concentration is increasing at only half the rate of the NO, and again we expect that because we need to have 2 NO2 molecules be decomposed for every 1 O2 molecule that's formed. So the rate of formation of oxygen is going to be half the rate of decomposition of the nitrogen oxide, or half the rate of formation of the nitrogen oxide, the NO. So, but let's go back to our rates. So because the rate is changing over time, the rate that we're talking about is the average rate over some period of time. So if you look at a time from, say, this point here to that point there, the rate that we're talking about is the average rate between those 2 points. We're not talking about an instantaneous rate, how fast the reaction is occurring at some point in between there. We're talking about the average between one red dot and the other. So the tangent to the curve at some point of interest, which is the slope at that point, is our instantaneous rate. Right? So the average rate is over some period of time, but the instantaneous rate is how fast is that concentration changing right now. And of course, 1 second from now, that rate will be slightly different. It'll be close, probably, as long as the reaction doesn't happen really, really fast. But the instantaneous rate and the average rate are not exactly the same. So also note that, that the production of O2 was slower than the production of NO, again, because we're producing half as much O2 as NO in our decomposition. So I already explained this, but we need to decompose 2 molecules of NO2 for every 1 molecule of O2 that's formed, and likewise we're producing 2 molecules of NO for every 2 NO2. So for every 1 mole of NO2 that we produce, or that we decompose, we produce 1 mole of NO and half a mole of O2. So if we now relate our rates for the consumption of NO2 and our production of NO and the production of O2, then because the rate has to be, the rate of reaction has to be the same, so we can say the rate is equal to negative change in NO2 concentration divided by time, which is equal to the change in NO concentration divided by time, divided by the change in time, and that's equal to twice the change in oxygen concentration divided by time. So that was reaction